Here's a part which shows several features which include drafts, tapers, fillets, and sculpted surfaces on the 3D model. The workflow is very similar to 2.5D milling. We will first define our stock geometry. We could start by defining a box as our stock material, specify the length, width, and the height of the stock material. Once we have a stock geometry defined, we could then define the machining origin. This can be set either to the part or the stock model, or you could even pick a point on the part geometry. We will now switch to the Create tab and choose from a wide range of toolpath methods that are available in VisualMILL. Primarily, we would start out with the roughing process. We're going to use a horizontal roughing. Specify a tool for the roughing operation. Determine the feet and speeds. This can either be set from the tool parameters or by loading the feet and speeds from a table. Define the clearance. The cutting parameters allows you to specify the tolerances, choose the cut pattern, define the step over control, specify your cut levels, which are your Z-level step downs. The engage and retract parameters allows you to specify the ramp motions for both core and cavities, and selecting generate, create your toolpath. The operation is now created. Selecting toolpath visibility displays the toolpath, and the toolpath can also be viewed in levels. So this creates a Z-level roughing toolpath. We will now switch to the Simulate tab to run the verification. Select the operation and hit Simulate to run the verification. And once the toolpaths have been simulated, the user could either program a re-roughing operation with a smaller tool and then process a pre-finishing or a finishing toolpath. For this example, we'll switch back to the Create tab and generate a pre-finishing toolpath using parallel finishing. We will use a ball mill for this application, specify feet and speeds, define the cutting parameters, where we could set the tolerances, the stock to leave, and control the step over parameters. And we'll define the angle of cuts as 0 degrees and select Generate to process the toolpath. The 3D finishing toolpath is now generated. You can zoom in to take a closer look at your toolpath. We will now run the verification by switching over to the Simulate tab. Select the operation and hit the Simulate button. This shows the verification of the cuts for the parallel finishing operation. The simulation could also be paused. You can hit Simulate through End to run through the simulation. Once the toolpaths have been simulated, we could go back and create additional finishing operations. We're going to create a Z-level finishing operation using 3-axis horizontal finishing. You could also specify machining regions that works as containment boundaries to limit the toolpath to certain areas of the model. We will still use the ball mill for this toolpath operation, specify the parameters, the step down and step over parameters, and generate the process of a toolpath. The Z-level toolpath is now displayed on the model, and you can run the verification of cuts from the Simulate tab. Select the operation and hit the Simulate button to run the verification. Selecting Pause and Simulate to End would run through the simulation. VisualMILL offers some of the advanced 3D toolpath methods like pencil tracing and remachining, which could be applied for cleaning up corners and valleys which could not be accessible by the large radius tools. In this example, we would like to apply a pencil tracing toolpath which would go around and clean up the scallops around the corners of the model. So I'm going to use a 3/8 ball mill, specify the cutting parameters, and selecting Generate would create a pencil milling operation. The pencil tracing toolpath is now visible, can be seen on the model. We will run a verification of the toolpath from the Simulate tab. The toolpaths are now being simulated. Selecting Pause and Simulate to End runs through a simulation. Now, what happens when there is a design change to the model? So let's go ahead and edit some of the features on the model. We'll modify the features on the solid model. And once a design change is made, you will notice that the machining operations are flagged, indicating that it requires a regeneration of the toolpath since the design in SolidWorks has changed. So we'll select the operation, right-click, and regenerate, and automatically recompute the toolpath. Selecting Post would output the toolpath for all the operations in the order in which they've been created. The posted output file can then be previewed in an NC editor. The backplot of the NC editor can also list the operation by tool types being used to program the part. So here's the preview of the pencil tracing operation. We will now take a look at an example where we have a mold which involves a draft. We can run some of the evaluation tools in SolidWorks to run some draft analysis and verify if there are any negative drafts on the model, and see how we can update the model by making design changes and generating the toolpaths. We'll go over to the Evaluate tab in SolidWorks and try to run a draft analysis. We'll specify the draft angle. I'm going to go with a 1/2 degree draft angle. Select the face, and from the draft analysis, you can see the areas shown in green show a positive draft of 1/2 degree, so there is no undercuts on the model. So the part can be programmed using a 3-axis toolpath method. I'm going to turn off the draft analysis, go over to the machining browser, and take a look at some of the toolpaths we've already programmed. So here's a remachining toolpath, which shows machining around the valleys for both steep and flat areas on the model. We will now apply some design changes to the solid model by modifying some of the features. I'd also like to modify the fillet features on the model by changing the fillet radius and making changes to the design would just require a regeneration of the toolpath in VisualMILL. Right-click and regenerate recomputes the toolpath. So going from a design change to generating a toolpath is a pretty quick process, which saves at least 40 to 60% of your programming time, as opposed to using a standalone system where you had to export the model out from SolidWorks and import it back into your CAM system to generate the toolpaths. We will now explore 4-axis machining methods. VisualMILL offers both indexed and continuous 4-axis milling. The indexed operations are performed using a table rotate operation, and you can apply a combination of both indexed and continuous 4-axis operations to program a part in VisualMILL. The part being loaded has features that needs to be programmed from multiple orientations. We will be starting out by programming this as a 4-axis. Under the machine setup dialog, we will choose the machine type as 4-axis, specify the rotational axis. This could be either about the A axis, which is typically the X, or it could be the B axis, which could be along the Y axis. Once you define the machine setup, you create your stock geometry. You would be starting out with a piece of block. So we'll do a roughing process by roughing the part from the top, flip the part over by 180 degrees using the table rotate operation, and perform a roughing operation for the other half of the part. So we now have a roughing operation created for the top half of the part. We'll switch to the Simulate tab to run the verification. Select Pause and Simulate to End to run through the simulation process. Once the toolpaths have been simulated, we will use a rotate table operation in here to have the part rotated over by 180 degrees using a table rotate operation, and then we'll program the roughing operation for the bottom of the part. The toolpaths are now visible. We will switch to the Simulate tab to run the verification of cuts after the part is being rotated. Selecting Pause and Simulate to End will run through the verification. The 4th-axis toolpaths can also be programmed by using a combination of indexed and continuous toolpath methods. So in order to create a finish operation, you would like to go back and apply a 4-axis continuous finishing operation. We will switch back to the Create Operations tab in the machining browser and apply a 4-axis finishing toolpath. The cut parameters can be defined to be either across or along the axis of rotation. The toolpaths can be contained axially by specifying low and high values and angular containments as well. And the user can also control the step distance for the step over. Selecting Show Toolpath Visibility displays the toolpath for the 4-axis finishing toolpath. We will now run the verification of the toolpath from the Simulate tab. Switch over to the Simulate tab, select the operation, and click Simulate to run the verification. The toolpath simulation can also be speeded up by selecting the slider bar located under the status bar in the machining browser. I would like to pause the simulation at this moment and take a look at the posted output. We'll select the machining operation, right-click, and Post. Will generate the NC file and can be viewed in an NC editor. The posted output file shows the rotational values for the A-axis going in from 0 through 360 degrees. VisualMILL also offers index 5-axis programming, which is also known as 3+2 machining. We will now take a look at an example how we could program parts using index 5-axis. VisualMILL supports a wide range of machine configurations. Under the machine setup, the user can select the machine type to 5-axis and choose a machine configuration as a head-head configuration, a table head configuration, or a table-table configuration, and specify the rotational axis for the primary and the secondary axis. The Set MCS operation under the Create tab allows the user to define the orientation of the tool axis. The orientation for the tool axis can either be defined by selecting a spin angle to rotate about, to rotate the coordinate system. Users could also specify a face by selecting a face in SolidWorks to pick a plane that represents the orientation of the coordinate system. And you can flip the normals by rotating the coordinate systems. Once the machining orientation is defined, you could select the Set MCS Origin tab to define the location of the machining origin. This could either be set to the stock or the part geometry, and you could choose one of the corners for the machining origin. Once the machining coordinate system is defined, you could generate a combination of 2.5 and 3-axis toolpaths. In this example, you will notice that we have a facing toolpath followed with a roughing operation, a horizontal finishing, and a drill operation. Once the operations have been programmed for the top face, you could use the Set MCS operation to reorient the coordinate system to program the front face using a combination of 2.5 and 3-axis operations. You could then reorient the coordinate system to the side face to program the operations to the side and the back face of the part. We will now run the verification of the toolpaths from the Simulate tab. We'll select the machining operation set and hit the Simulate button to run the verification. The operations are now being simulated from the top face. Once the operation for the top face have been simulated, the simulation for the front face, followed with the simulation for the right and the back face of the part. So you can program and simulate and verify from multiple orientations. This concludes our demonstration in SolidWorks VisualMILL. I would like to hand it back to Jerry.
Thank you, Uday, for that demonstration. A couple questions have come up that there were some delays on the video. We apologize for that. This video is actually going to be available through the SolidWorks website and our website as well, so there shouldn't be any delays. The other thing to think about is we can do custom presentations and demonstrations for those that are interested, and those should not have any delays.